Hi, let's continue talking about matter and measurement. So I want you to read what's going on here in this image. Just to be absolutely clear, what is in this watch glass is in fact just water. And this should actually kind of lead you to a couple more questions. Since it's just water, we can say this is a pure compound. That said, I still see more than one thing present. There's bubbles. It does look like there's liquid underneath those bubbles, underneath that surface, and there is in fact a little bit of solid present too. Which is interesting. Now, since this is just water, this should yield another question, because now there's more than one way to categorize matter, in that not only is it what is the matter made of, what phase of matter is present. So this is our image from before, and all of this is still true about how to classify matter, but after we make this classification of what type of matter is present, we can also take the step to say something that we're going to call phase or state. Now, as with before, these phases, these states, there are macroscopic properties, there are microscopic properties, and there's a way to represent it on paper, as you may remember from our first lesson. So the first, we're just going to go through the macroscopic. These are not our atomic or symbolic. We're going to say that solids, by definition, is matter that has a definite shape and a definite, I can't spell today, volume. So a good example of this would be like a metal ring. The shape of the matter does not change wherever the matter goes. Now, I'm not talking about like hitting this with a hammer. I'm just saying as it is at rest. The shape is definite, fixed, constant. The volume, the amount of matter, the amount of space this matter takes up, is also constant. So this would be like, for example, if we took some sort of a metal cube and put it in a container, it stays a metal cube after some time has passed. For liquids, the shape is now indefinite. This means that, well, it's variable, so that if we can put this in a container, we pour our liquid in. Oh, I don't know. We've got a cup here, and the liquid's coming out, right? And then sometime later, the liquid has now changed in shape, and it's now filling up the bottom of the container. That said, we're going to define a liquid in contrast to a gas that the volume is definite as well. In relation, well, the volume is definite as well, relating it back to solids. For gases, this is kind of interesting. The shape is, of course, indefinite. In much the same way as a liquid, you put it into the container and the shape of the actual gas itself changes. But more interestingly, the volume is indefinite as well. This is the kind of thing you see when like vacuum pumps get involved, or this, oh, did I click too many buttons? I did. When there's vacuum pumps involved, or high and low pressure environments, that the like a balloon that's sealed can actually change in size even though no matter is going into or out of the balloon. That's what I mean when I say indefinite volume. So working a little bit further, to both the atomic representation and the symbols, for a solid, the best way to show that a solid is in fact solid is to show a large number of tightly packed, so tight, regular packing. So this like semi-regular shape that's in the bottom of your container, but it's not taking up the whole bottom. I realize that if like you really zoom in, there's the hypothetical situation where like the solid takes up the whole container. So this would be a solid as well, I guess. But better to show the first representation to show that the solid's there and it has its own shape and it's not so zoomed in that you can't tell the difference. And if a substance is in fact a solid, we're going to represent it as S in parentheses. I did say substance, so this is really a way of referring to elements and compounds. So for example, you might see something that says like, this is iron, solid. We'll deal with the symbols on the next slide. For a liquid, it's a little bit harder to show because you can't show motion. I don't want to show motion in these diagrams. So really, I think the best thing to do is to put a bunch of matter on the bottom of our container, but then try our best to not show that it has some sort of regularity. And that regularity, I don't know why it keeps moving. And that regularity is also represented in referring to solids as having a crystal. Oh my God, my writing is not good today. Let me clean that up. All right, it's got a crystal structure, sometimes referred to as a crystal lattice. And lattice just means like, I must have pressed the button. Lattice just means like a regular structure repeating over and over again, like lattice work like is a fence where it's like the same shape over and over and over and over again. The liquids do not display any sort of crystal structure, and that is their difference between solids, against solids. As a symbol, you would put an L in parentheses, but to make it not look like a 1, I prefer to show a cursive L to make that delineation. You don't have to, I just choose to. Sometimes I'll put it italicized on a piece of paper. And then for gases, what we want to show is in our diagram that the particles are spread out over whole space. So they're taking up the whole container. There's a click region on this, and I don't know why, and I'm going to try really hard to not click. There we go. But clearly you know what's coming next. But these particles are not remotely close to in physical contact. They are not, they're taking up the whole container. So they're not just at the bottom of your container. There's no regularity to their shape. So that's how you would represent a gas. Now we can do this, I'm just showing an element here, but obviously you can show a particle diagram of a compound gas just as easily just by making sure, that the particle looks a little different. We can still make that change. And then the symbol to show a gas is just a G in parentheses. I'm hitting something. I think maybe I'm picking up my pen too much. Okay, I'm going to keep the pen low, and hopefully that doesn't change anything. There is a point of order here in that I said that substances, this usually refers to substances, there is one specific mixture that is so common in our experience that we did give it its own symbol. So sometimes the symbol AQ will be shown next to a compound, and this means aqueous, which is code for dissolved in water. So the nomenclature there would be to say something like sodium chloride, aqueous, with a little AQ parentheses as a subscript, and this would be an indicator to you to say, there is water present. In fact, that is a way to show a mixture that is a little different than the way to show mixture that we saw before. And then to round things off today, I just want to talk a bit about chemical formulas and how we represent on paper the other half of things. So we've seen particle diagrams for compounds. We have these symbols that we can put next to them, but we don't have the actual chemical formula that we've talked, that you're probably familiar with. We haven't seen those yet, so I wanted to talk about them briefly. This, in general, if you have a compound, this will communicate how many and what types of elements are present in your compound. There will be numbers, and these numbers may or may not be in what we would call a simplest ratio. You might see a 1-to-2 ratio. There might actually be a 2-to-4 ratio, and depending on the situation, that's fine. But for elements, the symbol is very simple. First letter is capital. Second letter which is optional, is lowercase. So sometimes you'll see something like a W or an F. These are chemical formulas. They're chemical formulas for an element where there's only one letter as the symbol. At most, 2 letters. I'm going to put a little asterisk there because that's not always the case, but I think the way the periodic table looks now, it is the case, so there's nothing to worry about with that. But you can see these guys here have one of each. I picked up my pen too much. This is strontium, calcium, tungsten, and fluorine, respectively. Some of the element symbols are rooted in Greek or Latin names because they were very old. The chemicals were discovered a very long time ago, and that's why they don't match, like W being tungsten. Tons of fun stories there, but that's for another day. For a compound, like I said, it may or may not be in the simplest ratio, but since we have more than one element, we're going to see a combination of capital and lowercase letters. So this being two compounds, sodium chloride, sodium and chlorine. This one here is one calcium atom and two fluorine atoms. That's what comes together into that formula. That's what this 2 means. Subscripts follow symbols. They refer to. So this 2 applies to the F. This 2 does not apply to the CA. Sometimes you might see these big numbers out front. I'm going to change color to make sure my writing stays consistent. Sometimes you might see this number out front. That's what we're going to call a coefficient. I'm going to turn on the light. And coefficients work the same way as subscripts, except subscripts, so coefficients apply to the whole formula. So this 2 applies to the H's and the O's. So this, as it's written, is actually 4 H's and 2 O's. So that's, the difference is the coefficient applies to say there are multiples of the same particle over and over again. So the idea there would be that this would be like showing 2 particles where that H2O is upheld. Like I said, you may or may not see these these lowest terms ratios. And then the last thing I'll mention is sometimes you see parentheses followed by a subscript, and you do have a distributive property there where this does get distributed onto both, and this 4 only refers to the O, so this is going to be 2 P's and 8 O's, and I guess 3 Mg's to be consistent and complete. One final thing to mention is that for mixtures, since there is no fixed ratio and no chemical bonds, you do list all of the different compounds and elements that are there. So what all we're going to do is put a plus in between to say this is and. This plus means and. Sodium chloride and calcium fluoride. So in a container, you would maybe see 2 different kinds of particles, and I guess I should represent the particles slightly differently to make sure we're delineating sodium, chlorine, calcium, and fluorine separately, but that would be what it would kind of look like in the particle diagram. Don't forget that when you have an aqueous solution, this is kind of like writing KCl plus H2O, except we're going, that's that AQ, that aqueous is shorthand. So just to sum things up, lots of letters, you know, capital followed by lowercase, and these symbols can refer to phase of matter. We can represent our particle diagrams to show how the particles are packed, or we can just say in words that it's definite shape and definite volume. And don't forget that, that this applies to liquids and gases with stuff that was shown on the previous slides. Thanks for watching.